Hi, welcome back and thanks for watching again. This is going to be part 3 of my video series about building your own overdrive on a breadboard. And so if you followed along the first 2 parts, this is going to be part 3 and we're going to be looking at ideas for modding this pedal further. Just some simple stuff that we could do to change the tonality of this pedal, just stuff that is pretty common when modding pre-existing pedals. And I'm just going to talk through some simple concepts that can be applied to not just this pedal but other pedals as well. And I will talk just a little bit about some of the electronics and the theory that goes on behind it, but for the most part it's going to be about just talking through some practical examples of modding or changing the tone of this pedal. And I have several loops set up so that we can play the loops back to back as we change different components, and you'll get to hear exactly how the tone of the pedal changes. So let's just dive into that, and I hope you enjoy the video. Okay, so we're back and taking a look at the schematic. I think we can break this up into about 5, maybe 6 components, and I'll mask them out in the screen, but this one here first is going to be our input. I won't really explain everything right now, so let's just go briefly through each component. And this part here is going to be the first gain stage and the clipping stage. This is where it all happens. This is sort of the heart of this circuit. This is where all the good stuff happens. Probably the most important part of this whole schematic. And then this part is going to be our tone knob. So this is where we shave off the high end, and I'll explain that later. And then this part is going to be a second gain stage, a very simple second gain stage compared to the first part, but it's doing the same thing. And this part is our output. And so those are the 5 components to this circuit. And then up here on the top left, this is our power supply, and that has some importance as well, so we'll briefly talk about that later. So that's basically the 5, or I guess 6 components to this schematic. And so the next thing we'll talk about is this guy. Let's see if we can. Okay, and so this is what's called a simple RC filter. RC just stands for resistor and capacitor. And so here you see a resistor, and then there's a capacitor, and then there's a capacitor, and there's a resistor. And so the signal would be traveling from here, passing through this way, same over here. And I've written below what each of these do. And so when you have a resistor in your signal path and then followed by a capacitor going to ground, that's going to be a low pass filter, meaning that it's going to pass low end, or you could call it a high cut filter. It's going to cut high frequencies. And so when the opposite happens, where you have a capacitor in the signal path followed by a resistor going to ground, you're going to have a high pass filter, or you could call it a low cut filter. The cutoff frequency, if you wanted to calculate that, is in this equation here, and that's a pi. So it's 2 times pi times the resistor value times the capacitor value, and you take that all and then divide 1 by that number. And you have to be careful here because especially the capacitor, when we talk about capacitors, remember we talk about microfarads or picofarads, and so those are really small numbers. And so if you're talking, say you're talking about a 0.01 microfarad capacitor, that's actually going to be 0.01 multiplied by 10 to the negative 6th order. That's going to be a microfarad. So you have to plug those numbers in correctly to get the actual cutoff frequency. Same with the resistors. If it's a 4.7K, that means it's a 4700 ohm resistor. So you gotta plug those numbers in as well. The cutoff frequency is where it starts to taper off. So I'm not going to draw it. You'd be best to look it up. There are going to be plenty of articles and stuff you could find online talking about the RC filter, but it's not like it's going to suddenly cut off everything below that frequency. So it's going to be a gradual cutoff, and you still are going to hear stuff below that frequency even if the cutoff frequency is above it. But let's go back to the schematic, and if you look here, I guess I can't get both on the screen, but let's look at this right here. It's a high pass filter, and if you look right here, this is the same thing. So you have a capacitor in the signal path and a resistor going to ground. In this case it's going to the reference voltage, but it's more or less for the sake of this argument it's going to be ground, and so that's going to be a high pass filter. And with these values, it's not really going to cut off a significant amount of low frequencies, especially when we're talking about guitars. So these values are not going to impact the guitar signal a whole lot. So basically, you're getting almost all of the guitar signal going through here. If you were to make this really small, like a 0.001, so make it 1/10 the size of this capacitor, you are going to see, or you are going to hear some of the low end get cut off, and it's going to sound a little trebly. But this really isn't here for the purpose of it being a high pass filter. It's mostly just to reference the reference voltage with the 1 meg, and this is going to set your input impedance along with the op amp's impedance as well. But for the most part, this is going to set your input impedance for the pedal itself, and then this capacitor is going to cut off some really extreme low frequencies, along with cutting off or stopping any DC current that could flow into the pedal. So we're going to kind of skip over this part. That's just the basic explanation of the input. You do need to have both here to have the signal come through properly into the op amp. But skipping on, let's go to this part without going into the main op amp section here. And so I don't know if this is in the shot, but if you look at that tone stack, it's exactly the same. It's an RC filter. And so this is just a resistor in the signal path with a capacitor going to ground. And like we saw earlier, this is going to be a low pass filter or a high cut filter. And when we built that pedal initially, changing or turning the trim pot for the tone knob sort of cut off a lot of the high frequencies. So you weren't really changing the low frequencies at all, but by turning the trim pot on the tone knob, we were able to control the top end of the signal. And so that's exactly what's going on. This is going to stay constant, but changing the resistor for the tone knob or the tone trim pot, we are changing the cutoff frequency for this filter. And so again, going back to the equation, and then again saying that this is going to be a constant 0.01 microfarads, but we're going to change this resistor between 0 resistance and then 20 kilo ohms. And by changing that resistor, we're changing the cutoff frequency, and so we are sort of moving the cutoff point. I don't know if this makes sense, but we are moving that cutoff point in our signal line. And so that's all that this is doing. So this is probably the most simple of tone stacks you could possibly build, but it's a very effective one as well. And then this is again the second gain stage, and then the output stage. The output stage is very simple. We have a volume pot, which is just a simple voltage divider. So it's just a very simple way of controlling how much signal comes out of this. And then this capacitor here is just another what's called a coupling capacitor, and is to block any DC current that might be coming through, and it's going to bring the signal back down to ground and pass through all the AC signal, which is our guitar signal. And so that's pretty much it. So the tone stack, the input part, and the output part, these three are really simple, and I'm just going to leave that explanation to that, and let's head on over to the main gain stage, which is where all the good stuff happens. And for that, Okay, so this is a very simple rudimentary non-inverting amplifier using an op-amp. So you have the signal coming in, and this is again the non-inverting input, if you remember from the second video. And then we have an output coming out of that, and we're going to feed back the output through a resistor into the inverting input, but also have another resistor going to, in our case it's going to the reference voltage, but you could have this go to ground. And the gain that we get from this type of an amplifier is going to be 1 plus the resistance value of R1 over the resistance value of R2. So just to make it really simple, say R1 was 100 kilo ohms, so 100K, and say R2 was 10 kilo ohms, so 10K. So that's 10 right here. And so it'd be the gain, the total gain of this amplifier would be 11. And what I want to talk about is this bit here. And this is a little difficult to grasp, so I'm not really going to go into the details of it. But by having a capacitor there, we are changing which frequencies are going to be amplified through this non-inverting amplifier. And if you're thinking why, the simplest way to say it is that this capacitor is acting as a frequency dependent resistor. Now that's not entirely true, and so if you want to go deep into that kind of stuff, please look up the word capacitive reactance. Okay, capacitive reactance, and that talks about how a capacitor works. You can go in deep and learn about the phase shift and all that stuff that happens, but for the sake of understanding why this is there and what it does, I'm going to simple it down and say that it is a frequency dependent resistor. And what that means is that, so we have a resistor here, we have a resistor here, and then we have another resistor right here. And when you have two resistors in series, which are when you have two resistors in line with each other, they add up. So the total resistance is going to be the sum of these two resistors. And in our case, if we have a capacitor there, and if we say, although it's not entirely true, if we say that that capacitor is a frequency dependent resistor, that means that the total gain of this amplifier is going to be different depending on the frequency, because the resistance ratio is going to be different depending on the frequency. And I know this might seem a little bit difficult to grasp, but what we're doing is, by having a capacitor there, we are changing the total ratio of this depending on what frequency is passing through this amplifier. And that's probably the simplest way I can explain this. There's a whole lot more going on. So again, if you are interested in doing a deep dive into this kind of stuff, please look up the capacitive reactance that I talked about, and then talking about non-inverting amplifiers and a bunch of stuff. So that is probably as technical as I will get in this video. Okay, so I hope that all made a little bit of sense. I've simplified it down quite a bit, just so you can get a grasp of what's going on. And these are clipping diodes. These diodes are what's going to cause the overdrive in the signal. I'm not going to go into the details of how these work, but by having two diodes back to back as part of the feedback resistor loop, you're sort of creating a level dependent feedback controller. I don't know if that just made it more difficult to understand or simplified it, but basically you're kind of controlling the amount of feedback that happens by the forward voltage of the diodes. If you're interested in how this works, definitely do some research online. There are tons of websites that explain this much better than I could ever do. But basically, these diodes are what's creating the overdrive. Okay, and so looking over here, we have pretty much this thing exactly. So in the first gain stage, we had a capacitor here, or here, capacitor here, and then also a capacitor going across, and then we had the diodes. It was all fancy and did a bunch of stuff. In the second part, the second amplifier we just saw, it is pretty much exactly this. It's just a straight up non-inverting amplifier. So you have one resistor, nothing else. And basically, it's just a very simple amplifier. And again, if you want to calculate the gain, it's this equation. And so if you look at this, this is going to be 2.4 plus 1, so 3.4 is going to be our gain of this section. What this is doing is you're going to lose a little bit of signal as you go through the tone stack here. This is a very simple tone stack, so you're not going to lose a whole lot of signal, and so it's a pretty efficient tone stack, but you're still going to lose a little bit of signal. And so by going through a second amplifier, you are going to be able to regain some of that signal that you lose, and then be able to have plenty of volume coming out of this pedal. And so now what we're going to do is I'm going to go in and talk about some mods that we can do and some components that we can change to drastically change the tone of this pedal. And so let's dive into that. I have several loops set up, and so we'll get to hear exactly how this behaves. Okay, so the first thing that we're going to modify or play around with is going to be this capacitor right here. And so in the following segment, I'm going to plug in different capacitors into our breadboard, and I'll have which value capacitor is in the circuit at the moment, and I'll be playing back a simple loop or several simple loops so you can hear how the bass response changes, and it changes quite dramatically. So this is really important to shape the bass frequency response of the pedal itself. Like I said, this is sort of a high pass slash low cut filter, but these values are not going to be cutting off a whole lot of low end, and most of the low end cutting happens here. And also it's better to have it performed here because that is tied in directly with the gain stage, and so it's changing how the gain reacts to different frequencies. So I'll be changing that, and you can hear what it sounds like. Okay, so I hope you were able to hear how dramatic of a difference those different capacitors made. Obviously, you can go in between because I did large steps, and so you can go in between and sort of fine tune it to your liking. This circuit is very, very simple. It's probably some of the simplest of an overdrive, a soft clipping overdrive that you could design. I guess you could get rid of this second gain stage altogether and go from the tone stack straight to your output, and that would make it even more simple. But as far as I could, when I first designed this, I didn't really design it. I mean, this is pretty much standard. It's not like an original that I came up with, but when I did design this, it was the simplicity that I was looking for. And so with this, you have so many options that you could do. You could add another capacitor here if you wanted to. You could do a bunch of stuff to shape the tone of the pedal itself. Okay, and so the next part that I want to go into are the diodes. And so we have two diodes going back to back. And what I want to do is we're going to add one diode on one side. So let's say this side. So it's going to be two diodes going in the same direction on this side, but only one on this. And that's going to be asymmetrical clipping. I did a whole video on total deep diving into asymmetrical clipping, so if you're interested, please go take a look at that. But we're going to do a simple 2 versus 1 asymmetrical clipping, and then after that we're going to do 2 against 2. So I'm going to add another diode on this end as well. So we're going to have 4 diodes total. Again, I will have what you're hearing on the screen so you can see what's going on, but we'll play with that. Okay, and so the last thing I want to do is I have another schematic over here, is this. Okay, so what this is doing is adding what's called a hard clipping section to this pedal. And so this is what's called a soft clipping overdrive. When you have two diodes, or it doesn't have to be two, but when you have diodes in the feedback circuit, the feedback section of an op amp. And in this case, you're having two diodes back to back going straight to ground, and the signal path is right here. So this is what's called a hard clipping setup. And why it's called that way is because this type of clipping sounds a little harsher than this soft clipping circuit. And so you're going to see a lot of hard clipping in heavy distortions, so like the Distortion Plus, the DOD250, the RAT, the DS1, the Marshall Governor, and a bunch of distortion pedals will usually use hard clipping. And oddly enough, the Klon, the famous Klon, uses hard clipping as well. But for the most part, you're going to see a lot of hard clipping in heavy distortion pedals. And so we're going to add a very simple hard clipping section to this pedal. The 1K resistor here is just to restrict the current flow through the diodes. Again, if you're building this pedal into an actual enclosure, it would be fun to add a switch to this so that you can have this switch on or switch off. I believe the King of Tone has a dip switch inside where you can turn on hard clipping or turn it off, or turn off this altogether and just have op amp distortion. And so those are very typical, common, fun switches that you can add if you're actually going to build this into an enclosure. But anyway, let's go ahead and play through some loops, going back and forth between hard clipping both and just soft clipping. And just for fun, I want to do one thing, which is have this capacitor be really large so that it's pretty much not cutting off any low end. It's still going to cut off a little bit of low end, but not a whole lot, especially in relation to the guitar's frequency range. And then I'm going to max out this, completely remove this, and what that's going to be is a full frequency overdrive. Let's just hear what it sounds like when you have a true full frequency overdrive. This is just for fun. Okay, so that's about it. I think we covered everything, and I hope I was able to offer some ideas as to modifications that we could do to this circuit. One thing I guess I didn't really talk about is the power supply over here. We're not going to go into the details of that, but basically when you have the op amp referencing real true ground here and V plus here, you need to have the signal that's coming in fall in between those two. So say this is your 9 volts, which is your V plus, and this is ground down here. You want to have your signal that's coming in run in between that V plus 9 volts and ground, so that it can wiggle up and down within those two, because of the way we have this set up. Sometimes in more hi-fi audio applications, you'll have a V plus and then you'll have a V minus. So this could be plus 15 volts and then there'll be a minus 15 volts down here. And in that case, your signal can be true ground, and no problem at all. But because in guitar pedals we're using a 9 volt battery most of the time, and so we have V plus and ground, you want your guitar signal to be in between those two, which is more or less 4.5 volts. And so by having two resistors of the same value and then coming off of that, this is going to be 4.5 volts. And then if you look over here, 4.5 volts through the 1 meg resistor, adding DC current to your incoming signal. And so what this does is your incoming signal that initially was running at ground down here, I don't know if this is in the frame, but it was running down here, but when it hits this part, it jumps up and now your signal is running at 4.5 volts. And by having that there, you are able to sort of use the full range of the op amp within the voltage that you have provided it. I hope that makes sense. I don't want to go too deep into that, but if you're wondering why this was there, you do have to have this here and then have the the reference voltage added to your incoming signal to be able to actually use the op amp in this way. So that's just a very quick, simplified explanation of how this op amp circuit works and what this is for. The capacitors here are to sort of stabilize the voltage and remove any ripples and whatever else. So I think that covers everything. I hope you were able to follow along. I tried to be as simple as I could, and so just have fun, and then once you start getting a grasp for how this all works, then you can start building your own stuff, modifying and designing your own circuits, and that's, I think, where all the fun begins. So I hope you enjoyed this, and please let me know if you have any more questions. Please share your thoughts in the comment section below. I'd love to hear what you all think, and as always, thanks for watching.